Alright, this is the video for Lab 9 for Math 215. And one general tip that I want to start off with is that a lot of the time in this lab we'll see this notation with like x sub j or maybe x sub 0 or x sub k plus 1, something like that. All that means is we have this variable x and we're going to change it a bunch of times. And just after j amount of changes, it's going to be x sub j. So like we always use x sub 0 to mean our initial x because it hasn't been changed at all. And so that's what that notation means. It doesn't mean that you're going to use a different variable necessarily. It means that they're both x, but one has been changed and one hasn't. And so yeah, let's start with problem 1. And for the first couple ones, I think 1, 2, 3, and 4, I would just very, very closely follow the power method that they give you. So yeah, first step, define an initial guess x0, which they give to you, is that. And honestly, what I would do for most of the labs is I would say x equals x0. So I can just work with this variable x. Because then, in the next step, when they say for j from 1 to k, compute x of sub j equals x sub j minus 1, x equals a times x sub j minus 1. Sorry about that. So you'll have a for loop for I in range, or for j in range, k. And here's the way that I would write this. What they mean with the whole different x sub k minus 1, is I'm going to create a temporary variable. And this is going to be equal to a times x sub j minus 1, or np.matmul a, and then I'm just going to use my x, because that's what I've defined so far. I don't feel the need to use anything else, because that is my x sub j minus 1, just because I'm going to use this x throughout the entire problem. I hope you can still see that. And then what I'll do is I'll say x equals temp. What I mean by this is I have my old x here, my x from the previous iteration, and using that I'm going to compute my new x. Another way that I could write that is just x equals np.matmul of a and x, but some people might find this easier to follow than that line. But this does the same exact thing. It uses this old x to reassign this new x, or in other words, our j and our j minus 1. So that's problem 1. Problem 2 uses problem 1, but it wants you to find out your first eigenvalue. And if you go up in the notes, it says that x sub k plus 1 is approximately equal to your first eigenvalue times x sub k. So we could condense that to x sub k plus 1 over x sub k is equal to our first eigenvalue. But remember, because these are vectors, you can't necessarily multiply or divide them by one another, and so they say to use the first entry, so x sub k plus 1 at 0. And the way that I would get these is, remember, by running your first one, your vector prox, you get an x sub k based on how many iterations you do. So you could say like, and I would use x sub k in this instance, meaning x after k amount of iterations is equal to e vector prox, e vector prox with 1. Oh dang, you guys can't see that. There. Sorry, that's not 1, that's k. Whereas x sub k plus 1, maybe something like that, or x sub k1, I think Python likes that better, is the same thing, except you plug in k plus 1. And then you just look at the first entries of both of those to figure out your lambda. And so that's how I do problem 2. Problem 3 will be very, very similar to problem 1, except as they defined in our power method, we want to do a bit of a different step. So inside our for loop, we want to say w equals a times x. And again, just for personal preference. I just like to use W rather than W sub j, because I feel like it gets more confusing the more underscores and different stations you use. So I'll do that, and then it says define x sub j, or x in this instance, as W divided by the magnitude of W, which you remember you can use np.linalg.norm of W for. But then, and then you'll return x at the very end after your for loop. But they also want you to return your eigenvector, or your eigenvalue, my bad. And they say the best way to compute the eigenvalue is by doing, let me just make sure I get this right. Yeah, they want you to obtain your eigenvalue using dividing the first entries of W and x sub k minus 1. And they say x sub k minus 1, so we want to look at this x rather than this x, because this is our old x and we're using it to compute our new x. And so in this spot right here, I'd say like our eigenvalue, I call it v, is going to be W at 0 divided by x at 0. And it'll use this x because we haven't assigned that new x yet. And so that's why I'm putting that line before that line. And so you return x and v. Problem 4 is very, very similar, but we're not using a anymore. We're going to use m. And rather than using this np.linalg.norm, they want us to find the largest absolute value in our matrix. And so the way that I would write that out personally is I would want to first take the absolute value of our matrix, which you can do np.abs of m. So that will return the same matrix except everything is positive. And then I would do the np.max of that. And so that would be some value, and I'd substitute that actually just right there for problem 4. And so that's all you have to do for problem 4. So yeah, and I feel like those first 4 problems are the toughest for the entire lab. Problem 5 wants you to do the ray quotient. So yeah, read about this in the book, kind of figure out what it means. But they just want you to run norm_approx_gen with the ones that you're given. So yeah, you're given your m, your x sub 0, and your k. So you can plug those all into norm_approx_gen and get some x sub k. And don't forget that when you run norm_approx_gen, I'm just going to call it that, you get x sub k, and you also get a lambda. So if you just want your x sub k, you need to say something like x sub k equals norm_approx_gen of that at 0, because you'll get 2 things and you only want the first. Remember that, especially for this problem and for the problems after it. And so once you get your x sub k, I would plug your x sub k into that r of x equals a times x dot all those things with a equal to m. And that should help with problem 5. It's not too difficult. And problem 6 is also very, very similar. Again, remember that your norm_approx_gen will return your x sub k and a lambda, but you only want this one. So say norm_approx_gen of all this stuff at 0. Okay, that's problem 6. I'm just making sure that I'm not missing anything. And then problem 7 and 8, yeah, are the last 2, and they go kind of hand in hand. So for problem 7, they want us to take an initial state and take this transition matrix that we're given and return it x or k amount of times, or after k amount of iterations. This will be very similar to problem 1, and because our matrix is defines a discrete Markov chain, we actually don't need to do any normalization or anything. Because these columns add up to 1, we don't need to do the normalization after each step. And so I would do something very, very similar to problem 1, where you have your initial guess. Just remember that your a in this instance isn't given in the, or your a will be that matrix that 0.7 or 0.7, 0.2, 0.3, and 0.8. So that will be your A, and I'm pretty sure you'll follow step for step what you did in problem 1. And you should get some values that are around like 78 and 118 for your final, just to give you an idea. And then for problem 8, they want us to run that with an initial guess of 0.6 and 0.4, and they want us to run it with K of 6. So I would just say something along the lines of, Netflix sub 6 equals subscriber values, and then you'd put in your inputs. I won't tell them exactly what they are, but they should specify in the textbook. And remember, again, your subscriber vals will actually return 2 things. It'll return the amount of Hulu subscribers and then the amount of Netflix subscribers. And you only want the Netflix subscribers. So for problem 8, you'd say Netflix subs equals subscriber values of all this stuff, but then you want the second value, so you'll say at 1. Remember that. And then lastly, for problem 9, they want us to deal with the certain chance of this frog leaving or entering certain ponds. And if you notice, in problem 7 and 8, when we were dealing with our Netflix, going back, Netflix and Hulu, going back to this matrix, and let me just make sure I read this off right. This 80% is people who are on Netflix and continue to use Netflix. Well, the 20% is people who have Netflix and will switch to Hulu. This one is people who have Hulu and will switch to Netflix, and this people is have Hulu and stay with Hulu. So remember that when you set up your transition matrix. And the matrix that they want you to set up in problem 9 is going to be very similar to this one, except it's going to be 4x4, obviously. But if we're setting it up, we know that the bullfrog is very likely to stay in pond A if he's in pond A. That's a 0.8 or an 80% chance. But here's the thing. These going across the top are he's in pond A and going to pond A, but then this next one, kind of following this pattern, is he's in pond B and wants to move to A, not A to B. This will be B to A. So our second value in this row is going to be the percentage chance that if he's in B, he's going to move to A, which I'm pretty sure is 50. And so I'll put that there. Likewise, the columns will be the chance that he's in A and wants to go to B, which will be a 5% chance, so 0.05. And this is B and B, so that will be 0.2. And so make sure you set up your matrix like that. Include the rest of those values there. But that should be it for problem 9, and that means the lab is done. Hopefully this video helped out a little bit, and I wish you the best of luck.